Hello, this is Eric from UNC Charlotte. MPI is often used to write distributed memory applications, and we will see today how MPI applications get compiled and executed. Lots of applications are written in MPI. Though MPI is not a library, it is a message passing interface. It is a standard which is discussed and published by the MPI forum. They adopted in June 2021 version 4 of the MPI standard, which is over 1,000 pages long. In the same sense that G++ and Visual Studio implement the C++ standard, or that Linux and macOS implement the POSIX standard, MPI has many implementations. General-purpose clusters usually use a portable implementation of MPI, such as MPeach or OpenMPI. But hardware vendors have produced implementations of the MPI standard that take advantage of particular features of the proprietary platform. MPI has language bindings for various programming languages, including C, C++, Python, Java, and R. But fundamentally, MPI is a C-style interface. MPI uses the most basic model of a distributed memory computer, a bunch of nodes, each with a single processing unit and memory, and they are all connected to some kind of a network. The execution of an MPI application is composed of multiple processes that all run within their own independent memory space. They have their own standard output and error output and environment. The processes run independently, but they also run the exact same code. The only way for one of the processes to know what it has to do is to know how many processes there are in total and which process it is in particular. The MPI standard can be hard to read. And while they are good books, the primary documentation of MPI functions is given in a set of man pages. You can find them on Google easily, but it is often useful to read the man pages provided by the implementation of MPI that you use, because it sometimes provides implementation-specific details. To know how many processes are part of the application, one uses the MPI comsize function. It takes two parameters. The first one is a communicator, which is a more advanced feature of MPI. In practice, we will pass MPI comWorld to indicate that we want information about the whole application. The second parameter is the address of an integer, where the function will write the size of the communicator, the number of processes that is in that communicator. We see here that MPI provides a C-style interface. The function takes the address of an integer as a parameter, where MPI will write the size out. And MPI will return an error code. A process will also need to know which process it is inside of the application. We will use the MPI comRank function for that purpose. It has a similar interface in that it takes two parameters, a communicator and the address of an integer. Let's look at a simple MPI code. All MPI codes have to call MPI init and pass command line arguments. This is part of how MPI sets up the different processes and configures the network channel between them. Also, all MPI applications will have to call MPI finalize. Failing to properly call MPI init and MPI finalize can leave the application in a partially initialized state, and undefined behavior can happen. So just initialize and finalize your applications correctly, and do not use command line arguments until after MPI init has been called. Then, each process will retrieve the number of processes in the application and the rank of that particular process. That information gets printed on standard output. In this demo, I am using OpenMPI. The way to compile a C++ application that uses OpenMPI is to substitute the compiler with MPI C++. Actually, MPI C++ is just a wrapper that calls an underlying compiler, and here it calls G++. Other implementations of MPI can use different tools for compilation. Sometimes the C++ compiler is called MPI-CXX instead of MPI C++, or even differently for proprietary implementations of MPI. Just read the manual of the implementation that you are using to learn how to compile your MPI application. To run an OpenMPI application, we use MPI run. MPI run will start multiple processes and initialize communication channels between them. The -np parameter enables to choose how many processes will be used. One can also use MPI run to execute on different machines, potentially on different continents. When started with 4 processes, the application will print 4 lines for the different ranks, because the application is composed of 4 processes, all running the same code, and all print a single line. We can similarly run the application with 8 processes or with 128 processes. Of course, in this case, all the processes run on my machine, which has a limited number of cores. But when on a cluster, OpenMPI will interface with the batch scheduler to know on which machines the application should run. That execution trace can make it look like the execution is not actually distributed. We can actually use OpenMPI to split the standard output channels of each process independently, and use some Unix foo to display the channels independently. When running the application, we can now see that each channel appears in a different window and clearly separates the execution in different processes. We can belabor that point by writing an application where each process waits a different amount of time and also reports its Unix process ID. When running the application with 4 processes, we can see that the different processes print their message with different delays, and they also all print a different Unix process ID. MPI can be used to program distributed memory machines. The programming model is that each process in the platform will execute the exact same code. A process knows what to do by identifying itself by calling MPI-com-rank and MPI-com-size. While the demonstrations were done on my own machine, MPI completely abstracts the execution platform. The behavior would have been the same if OpenMPI had been configured to execute over a cluster of nodes or on the machines which are distributed over the internet.